Hello, welcome to the lecture session. Can you all hear my mic? Please type yes if so. Okay, thank you. So similarly to the lecture on Wednesday, the recordings have already been uploaded. If you have watched it, then it's fine. You could probably just go to sleep now and come back in 50 minutes to an hour's time. Total length of the 3 recorded lectures is about 50 minutes. So I'll be playing them with a bit of breaks in between for questions and things like that. Most likely about 3:30, 3:40 we will be finished. Then we will discuss further things. Okay, so I'm going to start it now. If there's any problem with volume, too loud, too soft, please let me know in the chat and I will try to adjust. Okay, so let's do this. Okay, sorry, there's a technical issue here. I can't see my screen, so I need to do something else. 1 minute, 1 minute. Okay, yes, this works. So you should be able to see the screen. Now switching over in terms of audio. This is the second part of topic 4. We will talk about work cell support systems. And under work cell support systems, there's actually a lot of things to cover. You can see them listed here. I'm not going to read this out, and we will talk about this one by one. Okay, so first of all, we will talk about material handling. Basically, is when you move the things which you are working on, the parts, the products, the materials. So the definition given down there is where we move, store, protect, and control the materials throughout your manufacturing as well as your distribution process. This movement can be within your plant or warehouse, or between your plants, between your warehouses, or even up to the consumer. So design considerations when you want to do this: what are the characteristics of the material, the flow rate that you need, routing, where does it need to go, and scheduling, when does it need to go. We look at the plant layout. Different plant layouts, of course, require different sorts of material handling, and unit load principle, which is one of the most important things which we cover here. So characteristics, this should be quite obvious. If it is a solid, if it is liquid, we handle it differently. How big is it? How heavy is it? The different shapes can make it easier or harder to contain. The condition it needs to be in. Some things need to be refrigerated. Some things are dirty. There can be a risk of damage for fragile or brittle items, and there can also be a safety risk. Is it poisonous? Is it corrosive? Could it be explosive in the wrong conditions? Is it flammable material? So material handling equipment considerations is one of the more important things you need to consider when you're designing the layout of your plant, and different types of plant layouts lead to the need for different types of material handling equipment. So if you're having a fixed position project type plant, then you will use industrial trucks to move things around, cranes and hoists. But if you have like more of a job shop, those where we are focused on processes, maybe you could use AGVs, forklift trucks. If you have a product-centric plant layout, continuous or line, then you could use conveyors for more efficient product flow, but you will still need trucks to deliver different parts to different stations perhaps. So then we're going to cover what we call the unit load principle. Unit just means one. So a unit load is either one item, that's the simplest unit load, or you can arrange multiple units of an item and restrict their relative motion to each other so that they can be handled as a single unit with maintaining their integrity so it doesn't fall apart. Unit loads are used so that you could like handle multiple items simultaneously. This is good, especially with smaller items, because then you can have less trips. You can reduce how much time you take to load, unload, and reduce damage to the product. The unit load formation equipment is used to restrict materials so that they can maintain their integrity. So there's quite a few different things we will talk about here in the formation of the load. The first one, we are not even going to talk about it. If self-restraining or no equipment just means we take the item, and the item in and of itself is a unit load. But of course, that's less interesting. Let's talk about how we can create unit loads. So we could put them on pallets or skids, which are fairly similar, just slightly different designs. You should note that when you are having pallets or skids, there's a clearance at the bottom here, and these clearances are so that your forklift can lift them. Most of you would have industrial experience already. You have seen this. You can have slip sheets, which are basically thick pieces of paper or whatever material where you can place the load, and it's just to keep the load on one piece. Tote pans are basically like containers you can use to carry your items. Pallet or skid boxes, where these are reusable containers used to protect your loose items so that you can put it on a forklift, because obviously the size of the forklift is fixed. So pallets themselves are for use for items where you can stack, but if you can't, if you need a containerization for them, then we use what we call pallet boxes. Cartons, you all should be familiar with this as well, just boxes. You could use bags. Bulk load containers is for bulk materials. Bulk materials basically means things which are so small, or maybe they're liquid, that they need to be placed within your canisters of this. Okay, so they are generally bulk load containers. Crates are for discrete items. Intermodal containers, these are the containers which you see on trucks, and then there is a very standard size there because they can be used for shipping, and so that the shipping company can plan for all this. You can use strapping or tape or glue to what we call stabilize the load, put things together. There's also shrink or stretch wrap, where basically you are putting the pallet, for example, and then you just rotate it round and round, and the shrink wrap around provides a very cheap and easy to do unitization. So after that, there's no possibility of it falling apart. Okay. When we are trying to load up a pallet of various designs, you can do it manually. So that's what you see on the left. You can use robotic pick and place palletizers. This is fully automated, so you pick things off a conveyor, for example, and place it into a pallet, and when it is complete, okay, that's your complete pallet. Conventionally, we would use stripper plate palletizers, basically your conveyor system which feeds the product directly in the direction that it needs to go for palletization. So what is the direction it needs to go? There are quite a few different ways to arrange your items on your pallet. I wouldn't be explaining each of them, but you can see the difference based on what's the relative position of each item to each item. How do we arrange? How much packing do we have to do? So about the positioning equipment. Positioning equipment is used to basically manipulate your materials. You could be moving them, orienting them, loading or unloading them so that their positioning is correct. This is meant to ease and enable the handling material itself. So obviously, number one, which we're not going to talk about, is manual. So like you actually use a worker or use your hands to move it into the correct position. But there's quite a few different things we can talk about here. So when we are using these positioning equipment, besides the manual one, the job of the equipment is to raise a worker's productivity, to improve product quality and limit damage, especially when things are difficult to handle. Try and make sure there's no things falling which damages the product or damages the labor. And when we are doing positioning, it's also to reduce fatigue and injuries, which is why we try to avoid manual positioning, which can cause these problems. So some examples for positioning is we can look at this lift, tilt or turntable, which is just a system which, okay, you can place your material here and it will be lifted to the correct height to continue. Your dock leveler, most of you will have seen this. When you back up your truck in the loading or unloading bays, there's normally a raised platform, and the reason for this raised platform is so that the forklifts can enter the truck directly to remove your pallets. Now, not all trucks are exactly the same height, and so these dock levelers allow for slight raising or lowering of their hinges so that you can access, you can just drive in and out your forklift. Your rotary index tables, your ball transfer tables are other systems as well. So your ball transfer tables just allow manual transfer. So normally it's just going along the conveyor. When it reaches this part, you can easily move it off in a perpendicular direction. Your rotary index tables, you can see down here, each item is on a discrete panel, and it will move to the next discrete panel. And so you will position your processing equipment, your robots or whatever it is, above a particular discrete panel. So then the item will move, and then that's how it is being positioned. There's a parts feeder, what we use for small identical parts, and we want to do orientation in particular, or feeding them into a particular system. The movement of the parts is randomly channeled so that the orientation tends to come out together. So you can move them using vibration, gravity, air pressure. It's clearer just to show images really. So if you have something like nails, for example, and if you vibrate the container, then the nails will tend to travel outwards. And when it tends to travel outwards, then it will orient it, because it can't fit if it's not oriented in that direction. And so when it comes out of the feed, then they are all in the same orientation. There's a air film device which you can basically pump in just to precisely position your load, especially height-wise. There's a hoist, which is used for vertical translation. You want to lift loads, lower loads. A balancer is where you have a counterbalance weight used to support and control your loads, so that the operator who has to handle these loads only needs to guide the load and provide the position. They do not need to support the weight of the load. These manipulators, the rigid link, articulated jib, vacuum manipulator, these are used to lift as well as translate and rotate the loads, and these ones can be powered, but they're normally not automated. So these are manual manipulators. If you want fully automated, you would use industrial robots, as what we see on the right hand side here. Next, we will talk about conveyors. Now, conveyors are used when you want a high flow rate and you have a fixed path. This fixed path doesn't mean everything must go the exact same direction, but you can't move anywhere that you want that. So flexibility is fairly low. So conveyors are only used with sufficient flow volume. It does not make sense if you have less flow volume. You could just carry things, right? So there are a few different ways to convey to classify your conveyors. Is it handling unit loads or bulk loads? Is it in the floor, on the floor, overhead? In the floor basically means the conveyor is the floor. Okay? And whether you can accumulate, meaning your conveyor can have a backlog of items, or whether you don't allow accumulation, that it must always be flowing and that's it. So these are some examples of conveyors. There's a lot of examples. So your chute conveyor is basically a slide. And the properties of the conveyor, okay, yes, it can handle unit or bulk, it's normally on the floor, and it can be allowed to accumulate. So I won't mention these for the rest because they're all about the same. So you have your wheel conveyor and your different types of roller conveyor, quite similar. Rollers tend to be able to handle slightly more weight, and the roller ones can even be powered. So where the conveyor itself, there's a motor, and because of the rotation of the cylinders of the conveyor, so it's actually providing movement to the load items on it. There's a belt conveyor and a sled conveyor, similar as depending what is the thing which is helping to move. There is your chain conveyor. All of these types will have no accumulation, of course. Then your magnetic belt conveyor, where is for magnetic items which can be attracted by magnets. Your child belt conveyor is only for bulk item, and you can see that because of the different angles here, so that the bulk items would generally move towards the center and be carried through. There's a bucket conveyor for mainly used for grain and things like that. A vibrating conveyor is similar to a trout belt conveyor, but the items are not expected to just slide. Okay, so for items which have maybe higher friction coefficient and things like that, but as you vibrate, then it will tend to move downwards. So you use gravity and the vibration is to continue to move the items. You have your screw conveyor, which is normally used for bulk items, and as the screw rotates, then it forces the bulk items in a particular direction, depending on which way the screw is facing. Your pneumatic conveyor is basically for transporting items, basically pumping the items. Okay, so this is normally used for bulk items and not so much for unit loads. Interestingly enough, you can use pneumatic conveyors for unit loads, but it is not normally the best way to do things. Your vertical conveyors are how you translate your unit loads or your bulk in terms of the height. So you're going to a different floor for processing, or that your processing needs to start up higher or lower, then we will use a vertical conveyor. That's what we call a vertical lift, as well as a reciprocating vertical conveyor. There is a cart on track conveyor where let's say unit is already on a cart, and the conveyor system basically just moves the individual carts. So the conveyor itself, in a sense, has different units. The tow conveyor is similar in the sense that there will be different carts which are being, but the carts themselves are not powered, and so you will need to tow them. Okay. Trolley conveyor, these are all the overhead types of conveyors, as from 16 to 18, and generally with these overheads is by unit. And for trolleys, they just go round and round and round, sort of like your Genting Sky whatever thing, and there's no accumulation. However, you can have your power and free conveyor, which allows accumulation, so it allows to a bit of a backlog at a certain location, and your monorails, where each individual unit is powered by itself. Okay, the sortation conveyors, these are the ones that we see, whatever conveyor system where there are forks in the road, and so certain items, maybe item A will continue, but item B will shunted off to a different conveyor system. So you can also have item A and B coming from different sources and all merging. So we can call that portion where the merging is done the merge subsystem, and then the sort subsystem. When we are doing this sortation, how do we do it? We can use diverters. So there's a deflection diverter there. When the diverter is there, then it will push the item will proceed from the bottom right of this, and the diversion, it will be diverted into the correct direction. A push diverter, basically you have an actuator which will push the item so that it goes down a different conveyor, and there are different ways as well. You can use a pop-up wheel. So if the item is coming down, then when the wheel pops up, the wheel will tend to redirect the item at that particular time. So you just need to time it based on the arrival of the item. Pop-up chains are similar. The chains are normally underneath the conveyor, and so items can just move. But when the chain pops up, it can just push the item down. The sortation conveyor, these sliding shoes, these shoes are the things which we see at the side. If you can look at my mouse. And when the items come down the conveyor, then the shoes will move and just push the items over to the side. You can have tilting devices, where as the conveyor travels, if it tilts, then the item is tilted off and it will slide down. So if you have it on both sides, then we call it a cross belt transfer device. So the items are coming in this direction, and then it can go into various outputs. So obviously you will need to have logic here to handle this, but that is what will happen. So we will take a quick pause here, and then we will continue to the second section of this particular lecture series. Okay, so that's the first 1/3 of today's lecture. Thank you for your concern, but I'm not concerned about having any soft illness. It's just that at particular times of the day when it's cold, then I do have sinus issues. So that's the sound that you hear throughout the recording. At this point, I don't have, and yeah, no other issues or symptoms. Anyway, when you're stuck at home, there's not many people you can infect anyway. So any questions at this point? Please type your questions or use your mic as you want. Okay, so if there's no questions, then we'll just take a few minutes break. You may want to stand up and stretch. I'm not sure how you're getting your exercise nowadays. You may also want to go to the toilet for a while. I will give it just 3 minutes. I will assume all of you are near to stuff, hopefully, unless you're in a hostel. And then we will restart in 3 minutes. I will give warning when the time is coming. Okay, I see a question from Zehao. He says, how are we going to choose conveyor and the motor to run it? This depends very much on what you are transporting, okay? What you are transporting, how you need to transport it, what's the layout that you are using. So I've mentioned at various points, for example, if you have a project layout where you have something big that's central and all your movements around it, then you probably need trucks and cranes and things like that. If you have a continuous layout where the priority is speed, definitely you have to use conveyor, whether it's overhead, whether it's on floor, in floor, that depends on the material. So if you're doing bulk transport of liquid or bulk transport of grain, there will be different ones. The motor to run it, once you have chosen the conveyor, then you should just choose appropriately based on the load that it will need to be carrying. So these ones you will need to do your reading up. But that being said, you should note that when we are giving this type of assignments and when you are working on this in future, not just this but any other engineering design projects, there is no single right answer. And it is just as important what you choose as well as how you justify it. And you will find that the justification is what we are looking at. So choose something reasonable and focus on, is it justifiable? When you're trying to write a justification, then you might find that, hey, actually I cannot defend this. There is this disadvantage. Then you might need to change to something that you feel more comfortable defending. Okay, so if you take that sort of approach, then you will do fine. You are welcome. So I'm going to start the next video in 30 seconds. If anybody is listening into this from the toilet, you may want to make a quick dash back. Oh, but most of you are listening on your phone, so you can listen in the toilet anyway. If you're listening in the toilet, make sure you do not unmute your microphone. We do not necessarily want to hear any extra things. Okay, let me load up the video now. Okay, so here goes part 2. Again, if there's any problems with volume and stuff, just mention in the chat. Welcome back as we continue our talk on the work cell support systems. And we have already covered from 1 to 5, meaning up to conveyors. And now we are going to continue talking about the next thing, which is cranes. So cranes are used to move loads over either horizontal or vertical or a combination of paths within a restricted area, and is used when we cannot justify a conveyor. So as I mentioned before, conveyors are for high flow rates. The cranes provide more flexibility in movement. Welcome back as we continue our talk on the work cell support systems. And we have already covered from 1 to 5, meaning up to conveyors. And now we are going to continue talking about the next thing, which is cranes. So cranes are used to move loads over either horizontal or vertical or a combination of paths within a restricted area, and is used when we cannot justify a conveyor. So as I mentioned before, conveyors are for high flow rates. The cranes provide more flexibility in movement than the conveyor, but of course it cannot match the flow rate. So these are the different types of cranes: your jib crane, your bridge crane, stacker crane. All of them basically have similar functionality. It's just how we do the design. So your gantry cranes, most of you will be quite familiar with. The mobile gantry, you can actually push it around and it's not fixed in location. So if we want even more flexibility than what the cranes can offer, then we can use industrial trucks for your horizontal movement. And this includes movement from factory to factory, from factory to processing plant, from factory to processing plant to packaging plant and things like that. So this provides vertical movement only if the truck has lifting capabilities and is used when there's insufficient flow volume for a conveyor. So it also provides more flexibility in movement. This is the highest flexibility that you can have because the truck can be driven and moved around arbitrarily, really. So when we are differentiating the types of industrial trucks that we are using, does it carry a pallet or non-pallet loads, maybe a bulk load? Is it manual? Where is the truck manual, where you have to push it around, or is it powered? Is it a walking type, meaning that the user or the labor is walking alongside or with it to control it, or is it a ride type where the labor can actually stand on it to move? Is it stacking, no stacking? Can it only handle one unit load, multiple of them? Can it handle narrow aisles, depending on the design of your storage facility? Is it automated? And there are various levels of automations as well. Non-automated, then the labor cost is by far the highest thing you need to consider. For semi-automated, you are reducing the labor cost. So maybe the transportation normally is automated, but the loading and unloading is handled manually, so you need labor cost there as well. So for your storage and retrieval machine, you could have the man on board, but the actual loading and unloading could be automated. So both of these ways are possible. And if you want fully automated, you can use automated guided vehicles, which will have a higher equipment cost, but that means there's no direct labor cost. The labor cost is just in the setup and the maintenance and things like that. So your hand trucks are the simple ones, like basically to push things around. Your number 2 there, you have your manual and your powered pallet jack. So with your manual one, you literally just push things around and basically you're adding wheels to your pallet, and for your power one, there's a motor to help you do the pushing. There's a manual walkie stacker and a powered walkie stacker, and this one it gives some vertical lift to it so that you can stack. You have your pallet truck, platform trucks with rider or with walking. You have your counterbalance lift trucks for much heavier loads. You have your narrow aisle straddle as well as reach trucks. Basically, your straddle trucks will have to go all the way up to wherever you are depositing or taking a load from, and your reach truck normally they need to be much heavier because there's a bit more torque on this. But basically, it can extend into the storage or retrieval system or whatever it is. You can have a turret truck where there can be some rotation of the orientation of your load. Your order picker, your side loader, tractor trailers, personal and burden carriers. This one are heavily manual. It's just meant to provide power. So there are different type of trucks that you can use. Most of you will have seen these already, not very complicated. And now we want to talk about something which you may or may not have seen depending where you go for your industrial training, your automated guided vehicle. The whole point of AGV is it does not require an operator. And this is good for hazardous environments or environmentally sensitive environments, so clean rooms and things, because labor that goes in will need to clean properly, wear appropriate wear appropriate protective equipment, and also in environments where the labor cost is high. And almost all nations' labor cost increases over time as the nation develops. So eventually you start moving towards AGVs. So automated guided vehicles, they are good for low to medium volume in a medium to long distance random flow operation. So anytime you have fixed flow where you know it's going to start at A and then go to B and go to C, and that's one of the few ways that it always goes, then AGVs probably don't make so much sense. But when you want more random flow, where, okay, now I need this and here, now I need this and that, then AGVs start making a lot more sense, which is why you will see them use it in things like Amazon warehouses and Alibaba warehouses, because the flow of items from the source to the output, that is very, very random. It depends on users' orders. It's not something you can predict ahead of time. So for AGVs, there are two means of guidance. You can use fixed path guidance, where you have a physical guide path on the floor. You can also use free ranging, where the AGV has to do its own path finding. This makes it easier for you to change the path, meaning changing the path is just a matter of programming software rather than having to change your physical environment. But you need some sensors basically that you add in order to provide an absolute position estimate, because anytime you are estimating the position just from the machine itself, from the rotations of the wheel or whatever, you are going to have what we call dead reckoning errors, and there's no way to avoid this. So you do need external sensors just for the position estimates to be corrected. So these are tow type AGVs, where the AGV is a single unit and it pulls a train of trailers. Normally, you still have to load the trailers manually, which will still incur labor costs. So this is not very much used nowadays. Unit load AGVs are a bit more popular. Basically, your pallets are loaded, and these AGVs, they will carry these pallets around. So they are just responsible for the movement. There are different automated systems which handle the packaging, okay, or the filling up of the unit load. So your deck can include a conveyor so that it automatically loads from the source. So the AGV will pull up basically, and then maybe a pull up underneath the pallet, and then it might move up to lift, or it could use a conveyor to pull the load onto itself, and then it will go off. Typically, the size is 4 by 4 feet. Standardization of this makes it easier to plan automation. Okay, you can have an assembly AGV. So if you are building something big like a car or an engine which needs to go through multiple stations, this AGV will do the travel from station to station, and the product itself will be on the AGV through the entire process. Okay, there is a light load AGV for small loads, components, tools. These can be used basically when, okay, you need a user to request, okay, I need this batch of screws, and the AGV will be moving around and fulfilling the orders within the environment. This is not just in manufacturing environments, in your office environments, delivering mail and things like that, you can also use this. Fork AGV, you need counterbalancing, because obviously if you have a heavy load on one side, then you need a heavy load on the other side to balance it. You can have narrow aisle, straddle, side loading, and these are a bit more complex to design because they are interacting and basically having to be inserted into your storage area. So you need to make sure that there's no collision and things like that. Okay, which brings us to talks about our storage equipment, the equipment which we use to hold or buffer. Okay, so some storage equipment includes the transportation within the storage system itself. So here we see block stacking with no equipment, where we just load things up. But more normally now we have pallet racks. So you can see the design here. Basically, they're just like gantry design, and you place the pallets. These load supporting beams will hold the size of the pallets. You can have a single deep rack where every position has a single slot. Double deep, that every position has 2 slots, which means that your method of loading it, whether it's manual or automated, you need to be able to reach the second slot inside. Okay, the loads are supported by rails attached to the upright beams, and you can drive lift trucks between the upright beams in order to take out, to remove or to place in your pallets. So over here, what we see is our drive-in racks, but where you can access from both ends. The reason we want access from both ends, even though it uses more space, is this allows first in, first out. So you will not have the situation where your buffer, as long as your buffer isn't emptied, then there's something which stays in there indefinitely and never comes out. Okay, pushback rack. is where you place your load on an incline, which allows gravity-based movement. So basically, when you place the next load, it will just slide into position, waiting at the end, and all the removal is done from the same place. So similarly, you have the concept of a flow-through rack. You load it at the higher end, so you need some vertical translation. Place the unit load in, and the unit loads will slide down. And as you remove one, another will slide into its place using gravity. So sliding racks are where the racks themselves can move, and this can be great for space optimization. But of course, there's an additional layer of complication where you have to have actuation of the rack itself. Cantilever racks, as we can see here, are supported by cantilevered arms. Okay, these have slightly less strength, so you need basically stronger arms to be able to carry the same load as double supports. Your stacking frames are where you can basically create your storage in an arbitrary location by stacking up the frames for the pallets. Okay, your vertical lift modules, this is how we can place items into the input here, and then it will lift those items up, and then we can remove them and call the level that we need. Your bin shelving, storage drawers, you all should be familiar with this. Maybe some of you have this on your desk at home as well. Your A-frames is where units are dispensed from parallel arrays into a belt conveyor, and this carries them into your containers here. And so those containers are carried off by your conveyor. So these are also storage systems. Your horizontal carousel storage systems. So normally you will have a load unload station where you load, and then it will just rotate to give you free bins for inventory. They can be manually operated, but they can also be automated as well. And the space efficiency is good because you are only interacting with it on the long edge, and that's all. Okay, so when we're trying to, so all this storage equipment can be manual, but if we want to automate it, we have to integrate a sort of control system, a computer control system, where it handles both the transport, the storage medium itself, and just keeping track of all of these things. Okay, normally once you are automating it, you have narrow aisle because now nobody needs to go in. The system itself will move around to allow you to easily access what needs to be put in or taken out, and travel can be both horizontal and vertical at the same time if necessary. The advantage here is your labor cost. You need fewer material handlers, and there's better material control because automated systems, then you don't need to worry if someone's swiping some of your material. And your storage space use is efficient. Typically, the capital cost is much higher, and there is much more of a maintenance cost. If you have normal storage racks, there's really not much maintenance. Once in a while, you check whether it's breaking. Okay, but once you put in automation, then you have the regular maintenance costs. You have to check, and motors break down and says more often than your racks. And it's much more difficult to modify these type of systems. Basically, you design them and you're going to use them for maybe half a year. Okay, so your typical automated storage and retrieval system, you use racks which range between like 40 to 80 feet or higher for random storage. If you are using high-rise racks, really high multiple story racks, then you need tight rack tolerances and most importantly a level floor. Okay, and if you think about this a bit, you will realize that if your floor is slightly inclined, then obviously just a slight angle difference at the bottom will result in a high error at the top. Okay, because if it goes really high, then there's a bit of a tilt, and this increases the cost of the racks for high rise as compared to the basic storage rack. But of course, the higher you go, the more you can fit in the same floor space. Okay, the racks can be freestanding or used to support the building. So these racks are within the building. If you are building the building for this automated storage and retrieval, the racks themselves, because these are the strong weight bearing loads, can be used as your pillars basically for the building. In fact, there are designs where there is no building. What you're building is just the racks, and you literally just place a roof on top of the racks, and that is your building. And that means you do not have to construct a wall. The racks themselves are the support for your building. So your storage and retrieval within your automated storage and retrieval system will have to operate in an aisle where it serves the different rack slots. So the machine will have to traveling in the horizontal and vertical directions at the same time or individually. And so basically this carriage will have to go to your pre-programmed slot based on, okay, so right now I need this particular item. This item is in this slot. And so you will use a shuttle to transfer your loads and bring it to the delivery station, bring it to the place where maybe your tractor is waiting. So these are unit loads, automated storage and retrieval system, where everything is packaged into a unit load as we have described earlier. And maybe you have a fairly fixed weight. You have your stacking heights up to 130 feet high. Mostly we try not to go so high because the tolerances become much less at that side. Okay, so 5 to 6 feet wide aisles so that you can fit your loading machine inside. There are also what we call mini loads, automated storage and retrieval systems, where it's much smaller. So for smaller parts or bins, and for this, everything in the dimensions are much smaller, of course, and you can't carry as much load. Okay, how do we handle the control of your automated storage and retrieval system? It can be controlled by an operator, but most of the time it is complete computer control, and most of the time as well, the systems which we build are distributed, meaning like each storage and retrieval machine has its own dedicated computer, and there is a central computer which interfaces with each of these dedicated controllers. So you can think of each pair of aisles as one system by itself, and what you're doing is just stacking pairs of aisles together to make your entire ASRS. Oops, where's my mouse? Okay, so you can also have automated storage and retrieval systems where there is a man on board. So this will increase labor cost, of course, but a man is smarter than a machine. And so this man can handle the actual picking up, but the movement to place him in the correct position to be able to reach, that can be automated or manual. So he can just punch in, okay, I want 4D, and he goes there, okay, I pick up the item in 4D. Deep lane automation, storage and retrieval system. This is basically just a unit load ASRS, but you can store greater depths. So instead of single depth, double depth, or with some gravity load system, you can have like unlimited depth basically. And your rack entry vehicle is used to place it into the rack, and then perhaps there's a mini conveyor system inside as well to pile the racks together. Okay, so this is our discussion of your automated storage and retrieval systems. We will take a pause here before we continue to the final part of our lecture. Okay, so that's it basically for this lecture in terms of content. The last 1/3 of the lecture is basically worked examples, similar to what we're doing in the tutorial, but much more focused on the formula and the things that we are going to do. Give me a minute, I'm muting. Okay, so any questions for what we have so far? Is anybody still there? Okay, yes, so no questions. So as you can see, most of the stuff that we have covered today is basically just knowledge things. If there's things which are not clear, and especially now that we have the MCO and all, the terms that we use to call the different components, if you just go to YouTube and type those terms in, you will find real life videos of most of these things. So it's like, oh, what's a reciprocal, vertical, whatever. If you just search that on YouTube, you will see videos which will be quite useful for you to just understand what is capable. This will be especially useful because you are going to be potentially proposing some of this for your assignment. So it's worth the time to just take a look. Okay, so because of the nature of the third lecture component, I will just start that video directly. It's not factual things like we have in the first two sections, so hopefully people will not be falling asleep. Yep, so let me start that up. And okay, must remember to share the screen. Okay, everyone can see my screen, I hope. Yeah, okay, and switching over the mic and have fun. Now, for the final section of this lecture, we will talk about these things, our vehicle-based systems, and how we do some analysis. So we have talked a lot about the theory, the different options that are available, but when we want to do the design, what are the things that we need to consider, and what are the calculations that we need to make in order to decide, oh, what's the number, what's the spacing, and things like that. Okay, so this section is on the analysis of vehicle-based systems. What are our considerations? Guide path type. Is it going to be a fixed path on the floor? Is it going to be a rail? What's the type of vehicle? How we do routing and layout? What's the flow direction? Do we have docking points for loading and unloading? Where are there? How many are there? Number and locations of parking for the vehicles. How many vehicles do you need? What are the rules? What's the frequency of pickups and deliveries? These design considerations depend on your application, of course. Not all of these are flexible, and so you need to design to fit the constraints of the system. So when we are trying to do the analysis of vehicle-based systems, we normally try to simplify the problem. So in table 10.5, this is what we call a from-to chart. So how we read this is basically this first column here is where is it from, and the second column here is where is it going to. So these locations 1, 2, 3, 4, 5 are processing machines, loading or unloading stations. So maybe from 1 to 2, then we are looking at your flow rates, 9 times an hour, okay, and or 9 loads an hour or whatever it is. And then we are talking about our travel distance, which is normally just how many meters. So there's travel between 1 to 2, 9 times an hour, and the distance from 1 to 2 is 50 meters. From 1 to 3, there's travel of 5 times an hour, and the distance is further to 120 meters. So this is how we read this chart. You can also have a network diagram which shows between 1 and 2. Oh, that from not between 1 and 2, from 1 to 2. Okay, there's 9 deliveries an hour and 50 meters. From 1 to 4, there's 6 deliveries an hour, 205 meters. And these two are showing us the same information in a different format. And this can be useful for planning. So in this, the top one, the from-to chart, you get a better idea of the numbers involved. But in your network diagram, you get a better idea of the directionality. For example, here you can easily see that 1 is always a source. It is never a target. Similarly, you can see that from here, but it's less obvious just by looking at, 1 never comes out on this first column, okay, which is the 2 column. Okay, so now let's look at some of the formula. I say formula here, but these are not necessarily very complex formula. Basically, it's just how do we add numbers together and how do we calculate the rates of things. Okay, so we are looking at the delivery cycle time, which is basically the total amount of time taken to load, to move, to unload, and to move back. Okay, so this is a cycle. So you're loading somewhere, you go, you unload, and then you come back. This will give us your total cycle delivery time. Obviously, the time for movement depends on the distance moved as well as the speed of the carrier. So this is quite simple. So the available time per hour per vehicle, okay, can now be expressed using this formula. The 60 is just to convert it to hour, okay, because normally we calculate these dates per hour, but for cycle time, because cycle times are not measured in hours, so we are normally calculated in minutes or in seconds. Okay, so we need to do the conversion. So there's a conversion ratio here. Your AT is your available time, and your A here is just your availability. Availability is a measure of how often you can actually use the vehicle, taking into account downtime, taking into account charging time, for example. Traffic factor is a measure of how much traffic there is. If you have a single vehicle and it's never blocked, then your traffic factor is 1.0. But practically speaking, you have 10 AGVs. Sometimes one will have to wait for another, otherwise you have a collision. So that's a traffic factor. The more AGVs you have, the traffic factor will be slightly higher. And of course, you have your worker efficiency as well. Okay, how much you can rely on this particular worker. So your rate of deliveries per vehicle is quite simple. It's just how much available time do you have for the vehicle. So this vehicle is very reliable, unlimited battery. So for 1 hour, you have 1 hour, okay? And your delivery cycle time, which is computed by your previous equation here. So your delivery cycle time, let's say, is 5 minutes. And so 1 hour divided by 5 minutes is how many how many deliveries you can do per hour. Okay, workload is basically your flow rate multiplied by your delivery cycle time. This is the total amount of work that is accomplished by your entire system within 1 hour. So once you have this workload and you have your rate of deliveries for each vehicle, then you could quite easily calculate, oh, this is the number of vehicles that I will need. So I basically need, each vehicle gives me a certain number of hours for delivery, and I need this amount of workload. So I divide that, and this is the number of carriers I will need. You probably need to round up, obviously, because number of carriers is an integer. It's not a floating point number. Okay, so this is also equal to the total delivery requirements divided by the delivery rate per vehicle. Same thing. So once we have defined some of these formula, then let's look at how can we determine the number of vehicles. Okay, so if we have a layout, which I will be showing you on the next slide, vehicles are traveling counterclockwise around the loop. Loading time, unloading time is given. These are our parameters. So operator efficiency is just assumed to be 1.0, meaning no problems with efficiency at all. What are travel distances? What's the delivery cycle time? And how many vehicles we need to have 40 deliveries an hour. So this is our path, the loop, and the vehicles are traveling in an anti-clockwise direction. Here's our loading station, our unloading station, and as the AGV travels, we can calculate what's the distance based on this. So like 20 plus 40 plus 20, that's our unloaded. And here you have 35 plus 40 plus 35. Okay, so your travel distances for loaded and unloaded, you have 35 here, 40 here, 35 here, 20, 40, 20. And so this will allow you to calculate, okay, this is your loaded distance, 110 meters. Unloaded distance is 80 meters. We ignore whatever curves or whatever. So we are just trying to find a reasonable number, which is within less than an order of magnitude is accurate. So we determine from the layout 110 meters, 80 meters for loaded and unloaded. So this answers part A. What's the ideal cycle time per delivery per vehicle? And this one we are looking at, okay, we take 0.75 minutes to load, and this is our speed, which is 50. And so we divide the total distance travel by that speed. Then what's the time we take to unload? And then total distance for unloaded divided by the speed. If we add that all together, we get 5.05 minutes. Okay, this one is quite simple. Now, once we have this, we already know that, okay, we are going to spend 5.05 minutes per delivery. So if we want to make 40 deliveries per hour, what is the workload? So our workload is just 40 times 5.05, which is 222 minutes per hour. And our average time, so this is the formula that we talked about later. Efficiency is 1.0, traffic factor and all was given. And each vehicle basically can give us 51.3 minutes per hour. Okay, every hour the vehicles available for deliveries at 51.3 minutes. So how many vehicles we will require? We just divide this number by this number. And so the number of vehicles is 3.94, which should be rounded up, obviously. So you can't have 3 will not fulfill, so 4 will fulfill. Now, this is for a simple layout. What if we want to do our second example? What if we want to look at a more complex layout? And for more complex layouts, which are not just one cycle, then we will have to look, okay, so we have a station 1, which is our raw parts. Then it goes to either station 2 or station 3 or station 4. And then you have an unload station called 5, which receives the finished parts. These are the loaded and unloading times, 0.5 minutes. Production rates are indicated. some parts must be transshipped, meaning that it's not just from 1 to 3 and then to 5. Sometimes from 3 it has to go to 4 and then only it will go to 5. So vehicle movements are indicated. Let's determine first what's the average delivery distance. So this is your from to chart, and this is your network diagram. Here you can see the transshipment from 3 to 4, and then from 4 to 5. Otherwise, everything goes 1, 2, 5, 1, 3, 5, 1, 4, 5. But there is some transshipment here, only 2 an hour. The distance is 85. Okay, so this is the actual layout. You do not necessarily need to draw this, but this is normally provided for you, and then you can use it in your analysis of the system. Okay, so your proc is your processing operation, and mainly we just look at it as numbers. So your 2, 3, and 4, and your load and unload is here, and there's some manual operation which is at the load and unload. Okay, everything else needs to be automated. So first we are looking at what is the distance. Okay, and the distance is complicated by the fact that there are multiple paths that we could travel. Now, how do we handle this? We take what we call the weighted distance. So if you have 2 paths to travel, one path is 10 meters, another path is 100 meters. Then the average between 10 and 100 is just 55 meters. But that's assuming that you travel both of them equally. What if the 10-meter path, you travel it much more frequently, 10 times as often? Then we will take 10 times the 10 meters plus 1 times that 100 meters and divide by the weights, which is 10 plus 1, because you are taking total 11 trips. Of those 11 trips, 1 is 100 meters and 10 of them are 10 meters. So we add the total distance you travel and then divide by the number of trips. So then that becomes your average distance per trip. By the same concept, here's the numbers. We basically multiply the frequency, which we can get from the table, multiply that with your total distance traveled, which is 50 here. Okay, and when we do all of that and we divide by all the number of trips, then we find that the average travel distance is 103.3 meters. So having talked about AGV systems, let's turn our attention to conveyor systems, which are quite similar with just some slight differences which I'll discuss. This is a typical conveyor system. So perhaps you have a linear and a circular conveyor, and you have a robot which connects them. So you need to load from the linear conveyor, load it onto the circular conveyor. This is the layout of the linear conveyor. You can look at the resolver itself and the synchronization switch. So obviously when the part passes the synchronization switch, then that triggers, okay, now there is a loading which needs to take place. So when we're talking about the conveyor itself, if you have a single direction conveyor, the material travels at a fixed speed. Okay, the conveyor doesn't speed up or slow down. It's a fixed conveyor velocity, meters per minute. How long does it take for the material to move along the conveyor? That depends on how far you have to travel. The further, the longer. This is quite simple. And the flow rate of the materials is determined as well by the rate of loading. So these things cannot be very different. So your flow rate is how much the materials can flow, and you have a loading rate. So that loading rate depends on how long it takes to load, your VC, and your center to center spacing of materials on the conveyor. So if the conveyor has 1 unit at this position, how far before you get to the next unit? Okay, in the diagram it shows the cavities where your unit can be placed into, but of course it could be baskets or whatever things is on your overhead conveyor. Now the important thing here is if you calculate the loading time divided by the spacing, it must be less than your flow rate for the conveyor, which is basically 1 over TL. Why must it be less? Because if it's more, then there will always be, we haven't completed loading, but the next unit needs to be loaded now. Okay, and that doesn't make sense. And so this indicates why we normally want to use unit loads, because unit load principle means you can load multiple parts in a container rather than transporting part by part. And this changes our equation such that the flow rate is the number of parts multiplied by the velocity divided by center to center spacing. And so you can see that it's much easier to meet this rather than having to meet the velocity over SC that we have to meet. Okay, so in this example, the third example, a roller conveyor has a path 35 meters long, and you have a certain velocity, which is 40 meters per minute. So all the parts are loaded into tote pans, and there are two operators at the loading station. The first worker loads parts into tote pans. This one takes 25 seconds. Each tote pan holds 20 parts. The parts enter the loading station, and there's a 25 seconds cycle, so the parts enter every 25 seconds. The second worker loads tote pans on the conveyor. This takes 10 seconds. So with all of this, what's the spacing between your tote pans along the conveyor, the SC that we were talking about earlier? What's the maximum possible flow rate and the maximum time allowed for unloading? Okay, so let's take a look at this. First, the spacing of the tote pans. It takes 10 seconds to load a tote pan, but 25 seconds to load parts into the tote pan. Now, are these sequential and parallel? They're in parallel because they're being done by two workers. So the faster worker is constrained by the slower worker. So it takes 25 seconds. This is the loading cycle, the time which it takes. So the person who is doing the loading, every 25 seconds, he has to do it continuously. But the person who's loading the tote pan onto the conveyor, he does his work in 10 seconds, then another 15 seconds where he has downtime. He's waiting for the previous worker, the first worker, to load up the tote pan. So at a conveyor speed of 40 meters per minute, this tells us that our spacing should be 16.67, which is just 25 divided by 40, and then you convert it to between the minutes and the seconds. Okay, so this is our spacing. Given this spacing, what is our flow rate? And so we have our velocity, we have our flow rate. Now we need to see how many parts are inside the tote pan. Okay, so including that 20 here, it means that every minute 48 parts are traveling along this single conveyor system. Because there's 48 parts per minute, then the maximum allowable time to unload the tote pan, to unload the pan itself, not the parts. It depends with the flow rate of the pans themselves. Okay, so don't be confused between the part flow rate and the pan flow rate. And this flow rate is every 25 seconds, one pan will come along. And so your time to unload must be less than or equals to 25 seconds. If it takes longer than 25 seconds to unload, then you need to multiply the workers to do the unloading. Okay, so that's for a single direction conveyor. Continuous loops conveyors are similar, just slightly different. The complication here is that there's no stock of empty carriers at the loading station, and no loaded carriers are immediately available at the unloading station when needed. So how does this affect? Let's look at it. So we have our loading station, unloading station, and this is traveling in an anti-clockwise direction. So there's a delivery leg. The delivery is at the bottom here, and then there is a return leg where your carrier is empty. Considering your continuous closed loop conveyor, all carriers are emptied at the unload system. Now we need to look at a few different things here. So LD and LE we've already seen is the length of your delivery or your return leg. Your spacing is SC, then you have number of parts in system, number of parts per carrier, your feed rate, and your conveyor speed. So what is the number of carriers in the system? It's just the total distance divided by the spacing. This makes sense because they are evenly spaced. What is the total number of parts in the system? It's just the number of parts in each carrier multiplied by the delivery leg, because there are no parts on the return leg. So only in the delivery leg you have parts. So multiplied by this distance over your spacing. Okay, which is also equals to number of parts times the number of carriers in the system multiplied by LD over LD plus LE. So this is just replacing your SC here with NC over LD plus LE. Okay, and so your part flow rate is the number of parts in each carrier multiplied by your conveyor speed divided by your carrier spacing. This one is quite easy. We have seen this before, and this must be less than the number of parts per carrier over your TL. And TL in this case, obviously, is just the time which is taken to load. So once we have this, let's look at kiosk recirculating conveyor design requirements. If you have one load and one unload station, basically there are three rules which needs to be fulfilled: the speed rule, the capacity constraint, and the uniformity principle. So the speed rule says that your operating speed is determined by your carriers per minute. So the lower limit of this operating speed should be greater than or equals to the required loading or unloading rate. So if they are the same, then it's just the rate. But obviously whichever is the higher loading or unloading rate, then gives you a lower limit for your speed, and your upper limit is less than or equals to the capabilities of your material handlers. Okay, so the minimum is what is affected here. So this on the top here is about loading and unloading. This on the bottom here is about how much it can carry. And so these ratios are affected by both of this. This is what I just said, required loading rate, and the time required to load and unload the carrier. So the capacity constraint is that the flow rate of the conveyor must be at least equal to the flow rate requirement to accommodate reserve stock and to allow for time elapsed between loading and unloading due to the delivery distance. So this one is quite intuitive, that the conveyor must be able to carry enough such that there's no build-up at the loading and such that the unloading is fulfilled. Okay, so this one is interpreted as a system specification requirement. If you do not fulfill this, you cannot use this system. You have to change the system. And finally, there must be the uniformity principle. For the first two rules to make sense, your carriers should be uniformly distributed. Because if you have 10 carriers on the line of 100 meters and the first 9 carriers are 1 meter apart and the last one is just sitting by itself somewhere, then when it's not uniform, all our other calculations don't make sense anymore. So uniformity is a requirement just so that you can calculate your values so that you can apply the speed rule and the capacity constraint. So let's see how that applies with this recirculation conveyor. We can also call it a closed loop conveyor system. So you have a total distance of 300 meters, spacing of 12 meters. Each carrier has 2 parts. Time required to load is 0.2 minutes. Unload time also 0.2 minutes. The rates are defined as 4 parts per minute. Evaluate the conveyor system with respect to the 3 principles. So these values are given, extracted from the description. So let's look at the speed rule. The lower limit on speed is set by the unloading and loading rates, which are both 4 parts per minute, so the max doesn't really matter. So let's check 2 parts per carrier multiplied by 60 meters per minute over the spacing of 12 meters per carrier, and this is equals to 10 parts per minute. So basically what it is saying, it is more than our loading and unloading rates. So as long as it's more than equals to, no problem. Checking the lower limit. So there's the formula here. So we have 5 carriers per minute, which is less than or equals to 5. It's exactly correct. So the speed rule is fulfilled. And the capacity constraint, what is your conveyor flow rate? Okay, this is 10 parts per minute because we've already calculated this. This is substantially greater than the required delivery rate, which is 4 parts per minute. So the capacity constraint is satisfied. Okay, and uniformity is obviously satisfied because the question already says, oh, spacing is 12 meters. And we assume that this is uniformly loaded. We have made these assumptions in order to do all our calculations. So this last part was just talking about some of the calculations that we will need to do for this section. Okay, thank you for attending this recorded lecture, and we will see you for the next topic. Okay, see if there's any questions. I see one question from Wen Cheng. What is the min 5.5? Let me pull up my slides. Is the mean of the 1 over TL, which is the loading time, and 1 over TU, which is the unloading time. This is the rate of loading and the rate of unloading. So basically, it must be less than the smaller rate for loading and unloading. That's all. Okay, any further questions? If no further questions, okay, yes, Prasad, go ahead with your question. You can use mic or type, up to you. Well, min means the smaller one, max means the bigger one.
Papa, do you want, Papa, where is the triangle? Or where is the triangle thing that helps us play our song?
Yeah, so honestly, like I mentioned to you in tutorial, unlike other subjects where there's formula and stuff, for this particular section, the formula, it may or may not be helpful to memorize. Okay. The reason for this is quite simple. Each of these things are very logical in that sense. So, like for example, if we look at our speed rule, basically a speed rule correlates the speed with your loading and unloading rates. That's all. Okay, and your speed must be your speed cannot be faster than the loading or unloading rates. If it's faster, then it won't be able to load and unload fast enough. Okay, so if you think about it from that perspective, then you avoid the problem of I forgot exactly what formula we're supposed to use at this point. Okay, so that is one thing that for these it's actually fairly common sense and should not be a problem. So if both is 5, then it's 5. Yeah, so that's the easiest situation, easy for me also. Then whether is max or min is the same thing. No, these formulas are not provided if you have such question. Formulas are provided for things which you can't be expected to memorize. Okay, but all of these things are common sense lah. Put it that way. Yeah, well, put it this way lah. When we were doing tutorial 4 in class, that means not in the online learning one, every student managed to do and figure out every one of the questions, and this is before we did this lecture. Okay, I have confidence in y'all as engineers that this should not be a problem. Okay, any further questions? Okay, so thank you all for attending. As I said, University Senate was meeting this morning. I don't know why the announcement has not been made yet, but there will be significant announcements from Utah either today or over the weekend, or latest also will be Monday. When the announcement comes out, I will officially inform you all as well in the WhatsApp group as well as on Rebel. My topics have been completed for this subject. There is one more topic about safety, not a very long topic. Dr. Lee has already uploaded his videos for that, so he has asked you all to view those videos, and next week during the what's that called, lecture session, he will not be doing this playing the video for y'all the same as I do. So different lectures, different style. It will purely be for a discussion time for the safety aspect. So do expect shorter class, but do come as well for the time given so that you can discuss. In terms of the tutorial session, there will be no tutorial sessions on Microsoft Teams starting next week, but he will be available for consultation. You can contact him on Facebook Messenger. In Rebel, he has given his Facebook ID. Alternatively, you can message into the WhatsApp group. That will also go to him because I directly contact him by WhatsApp. So up to you how you want to contact him during the tutorial times next week. So yeah, so that's about it. How many chapters left? Just that topic 5. Okay, all mine is done, and his is topic 5. He will do next week, and then we will be complete in terms of the syllabus for this subject. Then you should focus on your assignments, your group assignments. I think the due date, I cannot remember exactly when. It's week 14 or something like that, sometime in April. So okay, Shaban to your week 13. Yeah. So yeah. So you will need some time to do that, obviously. Discussing tutorial 5, I think he's already put up the solutions, Shaban. So whether he will discuss in the same manner that I'm doing tutorial discussion, later 4:30 we have tutorial discussion, maybe not. I don't think, frankly, a lot of our lecturers are not very comfortable with this Microsoft Teams just yet. But he will definitely be available for consultation. So if there's no public class like this, just go and bug him and kacau him that he will do it. Yeah, no problem. Okay, if that's fine, then thank you all very much. I will be closing this particular session and okay, one test. Can someone try and mute me, please? Anyone? You're unmuting yourself, not muting me. Try and mute me. Cannot already, right? I found out the way. Okay. So anyway, we are going to close this. We are going to close this lecture. Please leave this lecture. 4:30. We will have our final tutorial. Okay. For those who want to attend, if you haven't attended any of the previous one.